In today's lecture, we're going to talk about multivariate ANOVA, specifically two-group MANOVA. And we're also going to talk about the difference between MANOVA, ANOVA, and a Ttest. So take a minute, open up the PISA 2012 dataset that we've been working with in class, the selected countries dataset. All right, so first, let's talk about the difference between multivariate, bivariate, and univariate. Univariate typically refers to simply one variable. So this might be something where you're just looking at a histogram of one specific attribute or characteristic of something. Bivariate data, on the other hand, bi meaning two variables, but in this case, really what we're talking about is two or more independent variables, but only one dependent variable. And that's why some people actually refer to things like multiple regression as univariate data, because they are using univariate in order to define the number of dependent variables. Correlation is another example of bivariate data. Multivariate data, on the other hand, involves multiple dependent variables and multiple independent variables. Thinking more about this, let's consider the difference between a Ttest and an ANOVA. And remember, we're dealing with just two groups. So a possible research question for a Ttest might look something like this. Are there differences in the mean PISA mathematics scores between Canada and Finland? An ANOVA question might also look like the same question. Are there differences in the mean PISA mathematics scores between Canada and Finland? They look the same because the difference between a Ttest and an ANOVA is that a Ttest can compare only up to two groups, whereas an ANOVA can compare multiple groups, two or more, but it can also just do two. So let's switch over to SPSS and do this and compare the results so that we can lead up to this topic of MANOVA. So here we have the data set, and actually in order to do this correctly, we have to prepare the data set for dealing with ANOVA. But first, let's go ahead and run the Ttest. So to run the Ttest, we're going to go to Analyze, Compare Means, and Independent Samples Ttest. So Canada and Finland are not dependent on one another. They're independent samples. And then we're going to take, bring this over here. The test variable is going to be PV1 math, and the grouping variable is going to be country. And notice it puts these two little question marks here. We have to click define groups, and we're going to tell it that, remember, we're testing Canada versus Finland. So group 1, and we have to type in the correct letters here. CAN is Canada in this data set, and FIN is the code for Finland. Click continue. So notice it puts CAN and FIN in here. Click OK. And then we can see it pop up here showing, first of all, notice the big difference in sample sizes. Not a big difference in means, 509 to 507. Standard deviations look about the same. Levine's test for equality of variances is statistically significant, meaning that these two countries' standard deviations are not equal. The variances are not equal, so we use the bottom row, a t-score of 1.6. It didn't really change that much. So this could be being thrown off by the large sample size. When we scroll over, we can see that it's not statistically significant. Mean difference of 1.8 points. That's not very much. So the answer to the research question would be no, but remember, the purpose of doing this is to compare the results between this and an ANOVA. So to run the ANOVA, I'm going to show you why we're going to need to do this. Compare means, one-way ANOVA, and what pops up in this little pop-up screen is we need to have the PV1 math in the dependent list, but this has to be a factor. So notice country variable doesn't even show up anymore here. So we have to create a new variable that's a factor. So in order to do this, go to transform, and we can just tell it to automatically recode. And what it's going to do is take the existing variable and alphabetize it, and then take the first one in alphabetical order and apply a 1. And the second one in alphabetical order gets translated to a 2, and so on until it is done. And there's only 4 countries. So if we go to automatic recode, and we can see we need to put the country here. And let's just call it CNT underscore factor. And click add new name. It fills in the blank. And then we want to start from the lowest value, which just means alphabetical order. That's fine. And then when we click OK, if we go back to the data set, you will see it listed here at the bottom. And in the values column, if you click those 3 dots, it tells you how it coded it. 1 equals Canada, 2 is Finland, 3 is Jordan, 4 is Mexico. And if we scroll to the right, it is selected as nominal. That's what we want, but these need to be numeric in order for it to be allowed as a factor. So if we go to analyze, compare means one way ANOVA, what's going to happen is when we put this in as a factor, you will see it no longer gives us an option to select the 2 countries of the 4 that we want to compare. Because of that, we now have to select the cases that we want to use. One way to do this is to create a variable that has 1s and 0s in it, where 1s represent the cases we want filtered out. So if we go to transform and recode into different variables, we can now take the country variable, and we'll call the new variable Canada underscore Finland. Click change so it fills in that question mark that was there. Click old and new values. And what we want to do is always we want to start with telling it to take system or user missing and translate it to system or user system missing. Click add. And then if the old value says CAN, we want the new value to be a 1. Click add. And we also want Finland to be translated to a 1. Click add. And then all other values we want to put as a 0. And this will allow SPSS to easily filter, so we can tell it if it's a 1, keep it. If it's a 0, filter it out so that we don't see it. And then run the analysis, we'll only see Canada and Finland. Click continue. Click OK. And now we want to test to make sure that this actually worked. So if we go to analyze, descriptive stats, frequencies, and what we want to do is compare country, and we also want to look at this new one called Canada underscore Finland, and we want to see if the counts add up correctly. So click OK. So you can see here, Canada had 21,544, Finland had 8,829, and Canada, Finland, remember we translated Canada and Finland both to 1s, so 30,373 people. And do these numbers add up? We can test that here. I've just opened a calculator. It's not showing on the screen, but 21,544 plus 8,829 is 30,373. So it has worked correctly. So now, if we go to data and select cases, we can use a filter variable. So click that, take Canada, Finland, and put it in there. And then notice output, filter out unselected cases. The unselected cases are those with a 0. So if we click OK, this is what we get, and we want to check to make sure this is right. So if we go to descriptive stats and frequencies and only put in country, if it worked right, we won't see Jordan or Mexico in this table anymore. And when we do that, we see that we only have Canada and Finland, and the sum of those is 30,373, which is correct based on how we filtered. We set up the filter. All right, now we can run the ANOVA. So if we go to compare means, one-way ANOVA, and then we can put the factor as CNT factor, country factor. And remember, this country factor already has everything filtered out. So right now there's only the numbers that represent the countries of Canada and Finland. So we're only doing 2 countries in this. Let's check some options here, see if there's anything we want to select. Let's select descriptive, homogeneity of variance. Let's go ahead and grab the means plot as well. And then let's look at Posthoc. Actually, we already know from the Ttest that there's an issue, but it wasn't statistically significant, so let's not bother doing this. Click OK. And we see here the test of homogeneity of variances. We see based on the mean, we get this 0.031, which is exactly the same as whenever we had the Levene's test for equality of variances, and that is because there's only 2 groups. So it's going to be the same. It's comparing the same 2 variances. We also see here in the ANOVA table the same exact p-value, 0.106, and that once again is because we're only comparing 2 groups. So if we scroll back up to the t-test, the t-score was the significance value was 0.106, the p-value. And then of course it shows these means plots, but remember the scale here is very small. It's only going up by 1, so it looks like it's a steep incline when really it's rather flat. All right, so now let's go back and think more about how this looks when we're thinking about MANOVA. So, univariate ANCOVA versus multivariate ANOVA. So a univariate ANCOVA involves 1 dependent variable, 2 or more groups, which is the independent variable, and 1 covariate. And the research question might look something like this. Is there a difference in PISA mathematics scores between Canada and Finland after explaining away variance in math accounted for by SES? In this case, the dependent score would be PV1 math. The independent variable would be the country Canada-Finland variable, and the covariate would be PISA's measure of SES, ESCS. The multivariate ANOVA, which remember we're doing only 2 group, so we're calling this 2-group MANOVA, 2 or more dependent variables, 2 or more groups. The research question would look slightly different. What are the differences in mathematics scores and in socioeconomic status between Canada and Finland? So in this case, we're not trying to separate them out. We're not trying to say what happens after the variance of SES is soaked up. We're actually saying, let's look at them simultaneously and see if there's differences anywhere in all of this stuff. So the dependent variable in this case is mathematics scores. We're going to use PV1 math. The second dependent variable is going to be SES. And then the independent variable is Canada or Finland. All right. So if we go back to SPSS now, go to Analyze, and General Linear Model. This is where we can find ANCOVA. So under Compare Means, notice that we can't add a covariate. If we go to one-way ANOVA, there's no place in here for a covariate. So we have to use this univariate here, and then we're going to use the multivariate in a moment. Under univariate, we have a dependent variable, fixed factors, random factors, covariates. The weight is not being used here, but we could actually use that with PISA. There are weights attached to these. So in this case, for the univariate, remember we're doing ANCOVA, the dependent variable is PV1 math, and SES is going to take the place of a covariate. The fixed factor is going to be our grouping variable, CNT factor that we created. And remember, we still have our file split. So that means that it's only going to be looking at Canada and Finland. We still have it filtered. All right, so if we go to plots, we can create a plot to show the CNT factor here on the horizontal axis, similar to the one we had for the ANOVA. So under plots, click add, click continue. Under options, if I can bring the window over here, we want to look at descriptive stats, effect size, power, homogeneity tests, and click continue. Click OK, and let's look at the output. So we can see the means here are small like they were before, 509 to 511. Levine's test for equality of variances. In this case, actually for the ANCOVA, it's showing that they aren't there's no statistical difference. So we can say that there's no evidence that there's an issue, and we're about to find out why. So if you see here, the CNT factor row, 0.038 is the F score, and the significance is 0.845. However, the covariate, SES, is highly significant. Partial eta squared is similar to the way that an R squared is interpreted. So about 10% of the variance in PV1 math scores is being explained by SES. 0% is being explained by CNT. So one way to interpret this is that when we ran the ANOVA without SES in there, there was a statistically significant difference between Canada and Finland. Once SES is accounted for, however, there's none. Actually, I take that back. There was none to begin with. So SES explains the difference, explains differences between Canada and Finland. There are statistically significant differences, but there are none once you look at the country. So SES explains differences in PV1 math. There's no differences between countries. And you can see here, I forgot to add the other one, but this is for PV1 math for country, Canada and Finland. I forgot to add the SCS one. We could have added that. Okay. Now for the MANOVA. If we go back to the same place, general linear model multivariate. And what we're going to do is, remember, this is a little different. We're not talking about what happens after SES has already explained some of the variance in math scores. What we're doing is we're testing differences between countries on both of these at the same time. So before, with the ANCOVA, we couldn't test differences between Canada and Finland on SES. Instead, we were looking at SES's relationship to the PV1 math only. In this case, we're not looking at the relationship between SES and math. We're looking at whether or not there are differences between Canada and Finland on both PV1 math and on SES. So the fixed factor here is going to be our CNT factor variable. Under plots, we can add CNT factor into the horizontal axis. Click add, click continue. Under options, we have the same options as before. Descriptive stats, estimates of size, effect size, power, homogeneity test. We should see something similar here. Click OK. All right. And notice we have Box's test of equality of covariance. Now, there's a big issue with Box's test of equality of covariance. In fact, most quantitative researchers do not ever use this test. SPSS simply has not removed it from its package yet. We're going to ignore that. We will talk later about that issue. All right, and there are multiple different ways of testing the multivariate relationship. I suggest reading about this in your book in the multivariate chapter. There are different reasons that we might use these. However, for now, because we only have two groups, we're going to use Hotelling's trace. You can see the F statistic is the same for all of these, and actually we're looking at country factor variable, not the intercept. But it's the same for all of them, so we should expect to get similar results. And the significance is 0, the p-value is 0. Partial eta squared is extremely small. 0.1% of the variance can be explained by group membership, whether someone is from Canada or Finland. And this is overall across both of our, both the PV1 math variable as well as SES. It doesn't matter which one, we're looking at both of them holistically across all of it. Kind of like how an ANOVA looks across all countries at once. Here we're looking at all countries at once and looking at these two outcome measures at once. Okay. If we scroll down here, we see Levine's test of equality of variances. Now this is for the ANOVA. So what happens is SPSS assumes that what we want to do is look overall across everything and then run an ANOVA, one of them for PV1 math, one of them for SES. So it's giving us these split up. You can see here PV1 math and there's the SES. So it's giving us the test of equality of variances for both of them. So you can see for PV1 math, there doesn't seem to be an issue. It's telling us that probably the variances are equal between Canada and Finland, but for SES, they are not. There are substantial differences between SES, between Canada and Finland on SES. And then we see the test of between subjects effects. This should look familiar because it's the same table that gets output for an ANOVA. In this case, we have two rows for each of these options, one of them for PV1 math, one for SES. So if we look at the country factor row, we see PV1 math has a p-value of 0.087, indicating that it's not statistically significant if we're using 0.05 as a cutoff. Whereas SES is statistically significant. So there's a statistically significant difference between Canada and Finland on SES. There is not for PV1 math. Whereas if we look back up here, we saw with Hotelling's trace, overall, there is a statistically significant difference. It just happens to be that that statistically significant difference is only for SES and not for PV1 math, which aligns with what we saw before with the Ttest and with the ANOVA, indicating there was no statistical significant difference between countries on students' mathematics achievement. Here we have the plots. Here's PV1 math. You can see it's a very small difference, actually, a little over 1 point, about 1 point or so. I think it was 1.8, wasn't it? And then SES, a lot bigger difference here. And remember, these are standard deviations. All right. So now that we have that, let's go back to our slides. So why do we bother with MANOVA then? Well, to answer that previous research question, you could run two t-tests. And remember, that question was, what are the differences in math scores and in SES between Canada and Finland? So we could run two t-tests, one to test the difference between Canada and Finland on PV1 math and a second one for SES. Same thing with an ANOVA. We could run two ANOVAs to do this. But these aren't recommended. And the reason is that running multiple analyses on the same data inflates alpha, or the likelihood of a type 1 error, rejecting the null hypothesis when you shouldn't, or finding a statistically significant result when in the population that's actually not there. And therefore, it reduces the power of your test in detecting a true effect. Also, running it as a MANOVA allows for analysis of differences simultaneously across all dependent variables at once. Once you see that there's an effect, then you're sort of protected from making those wrong decisions based on those p-values telling you there's a difference when there really isn't, because you already know there's a difference. Now you're just finding out where that difference is. The assumption, so for univariate ANOVA, you are looking for at least two groups in the dependent variable, an independent variable that's continuous, independent observations, no outliers within each group, normality within each group, and homogeneity of variance. For multivariate, it's kind of makes sense, I think, that there are continuous dependent variables, independent variable at least two groups, independent observations, that there are no univariate or multivariate outliers, which we can talk about later, but there is some different ways of testing multivariate outliers. Unfortunately, SPSS doesn't have any built in, but we can use something called Mahalanobis distances. Every time I say that, I just think of the Mummy. Then univariate normality, multivariate normality. Once again, multivariate normality, we don't have a good way to test for that in SPSS. So we sort of make an assumption that if there is univariate normality, that there also is multivariate normality. Homogeneity of covariances, that is an output put out for boxes M that we are sort of skimming over because it has some issues, especially with sample size, but there are issues for many reasons. There also should be a linear relationship between the dependent variables per group. A linear relationship, in this case, between SES and PV1 math. And there should be no multicollinearity. So how do we look for multicollinearity? Well, that would be a question of what if the dependent variables are highly correlated. If PV1 math and SES are really highly correlated, it might indicate that one of them is a proxy for the other, that they're measuring the same thing, in which case you shouldn't be running the MANOVA. You should just be testing an ANOVA on one of those things rather than both. So a best practice, sort of a guideline, is if the correlation is less than 0.6, you're okay. If it's above 0.8, then there's major issues. If it's in between, then you should be thinking about whether or not you should use them. Sort of questionable range. Partial eta squared, remember that is interpreted as the proportion of variance accounted for, similar to an R squared. So this is how we test for the effect size of the relationship that we're seeing. We want to see this be pretty high so that we can say that we are measuring something important or meaningful. So MANOVA is significant. Now what? Well, we already talked about these ANOVAs that get spit out that help us pick apart these differences. But when there's more than two groups, then that's whenever you do follow-up pairwise t-tests, which there is options for that in the Posthoc options whenever you open the MANOVA, the multivariate. And then alphas need correcting for both of those, so you have to select some options. And once again, I select using two keys if there are no issues with homogeneity of variances, if Levine's test says something positive. Another option, which actually is preferred by Andy Field in your textbook, Discovering Statistics, because MANOVA quantifies how well a linear combination can differentiate between groups. A discriminant analysis does a similar thing on a univariate level, and therefore it sort of matches better with the concept of MANOVA, while ANOVA does not. However, most of the time in the literature, you do see univariate ANOVAs being used and then pairwise t-tests, but discriminant analysis is another option that you can use, and we can talk about that in a future lesson. So that's it for today. I hope you learned something. please go back and rewatch this and kind of go through the motions so that you understand what it means to conduct a MANOVA in SPSS.